Hi everybody, this is David Brumley. Today I want to give you a quick research overview of our work on automatic exploit generation. This research project is joint with Thanasis Avgerinos, Sankil Cha, Brent Lim, Andrew Weesey, David Kolbrenner, Brian Pack, and Joe Minshew. I want to pose to you the following typical security task. This is a buggy program called iwconfig. It's found on many Linux systems. It's used to associate a wireless card to an access point, among other things. It's set UID root, which means it runs with super user privileges. And it's vulnerable to a typical security problem. Can you spot the bug? Now, most people with any security training at all pretty rapidly figure out the problem. Problem is the program starts executing at main, and it passes user input called argv1 to a routine called printinfo, which is passed to getinfo, which is then passed to string copy. And what string copy does is it copies that user input, here called ifname, into a local data structure called ifr.ifrname. Now the problem is this data structure is only 16 bytes long, and user input can be as long as the user wants. This is a typical buffer overflow problem. So for security people, spotting the bug is only half the story. The real question is how long would it take you to create an exploit? Now, I don't know how long it would take you, but I do know I give this sort of problem to students in my class pretty often. And it typically takes them between 10 to 12 hours to create a working exploit. Now, I know there's practitioners out there who can do it quicker. The quickest I've heard is 15 minutes. But it's typically a difficult problem. And the reason it's difficult is even for the most advanced security practitioner, even for people like Robert Morris, who's famous for writing his Internet Worm and going on to become an MIT professor, Kevin Mitnick, who was a notorious hacker who was on the FBI top 10 most wanted list, and Peter Mudge Zatko, who when I was growing up was actually one of my heroes. He was an open disclosure advocate, and he's a great guy. Really what they have to do is you have to sit down and think really, really hard about a program and figure out where the bug is. And then if you're security inclined, you have to think really, really hard about whether or not that bug can be exploited. And the reason it's difficult to figure out whether a bug's exploitable or not is reasoning about the source code is insufficient. You also have to think about how that program's going to run on a real system. For example, when I compile this vulnerable program on my computer, it compiles down so that there's a particular runtime state where there's a return address pushed onto the stack, and the ifr_name data structure is 68 bytes away. And a typical exploit would come up with user input that overwrites the entire buffer in addition to the return address. So when that getinfo returns, it executes bin shell. And the reason it would do that is an attacker would give carefully coded logic that would make the program execute bin shell, even though it wouldn't normally do that. And coming up with these sort of exploit strings is really difficult because it requires knowledge of low-level details, things like, well, assembly, stack frame layouts, and so on. So our project is automatic exploit generation. We want to take this process that's currently mostly manual, and we want to figure out the computer science principles and algorithms to make it automatic. More simply, given a program, we want to be able to automatically find bugs. That's been done before. And then we want to do what hasn't been done before and demonstrate whether or not those bugs are exploitable. So given a program, find bugs and generate exploits. Let me show you what I mean in a real-life example. This is the iwconfig program that I've been showing you all along. It was compiled from source. You can see here the string copy, just like I showed you. That's the vulnerability. The total source is about 1,400 lines of code. That's not including libraries. So what we do is we run our utility called AEG, which implements our techniques. And it does things like analyze the program to find the bug, that's shown here, figure out that the return address is 68 bytes away, and actually generates an exploit string. And it does this in about 0.7 seconds. And so if we actually look at what this exploit string is, this is what it looks like. The important thing, though, is what happens when we run the vulnerable program on the output of the utility. We actually get a root shell, and it's as simple as that. So we automatically got a root shell, and it took us about a second. That, to me, is one of the very exciting things about this project. We've taken something that requires really smart people to think really, really hard, and we've come up with an algorithm, and we can do it actually relatively quickly. And to me, that actually has important security repercussions. It means those people who previously took hours and hours and hours to create exploits can now do it much faster. So of course, we now need to consider that possibility when creating defenses. So what is our research program? Well, we really have a tiered approach. The first thing we want to do is we want to be able to characterize mathematically what it means to exploit a system. So I call that exploit theory. Our current approach is once we characterize things mathematically, we use formal methods to check whether or not a program is exploitable. Now, we don't just apply formal methods and expect them to work. Typically, you run into many, many challenges, and so what we do is we leverage source code and binary code analysis to inform our formal methods to make them scale and work in our problem setting better. We then, once we build this infrastructure, have these formal methods and have this theory, come up with specific applications like that AEG program I showed you. We actually spend most of our time looking at formal methods and source and binary code analysis. That's actually the hard part. Building these applications, once you get that right, is not so difficult. So the first question is, what is an exploit? Well, to give you an idea of how difficult this question is, go out and ask a number of people what it means to exploit a system. For example, if you went out and asked the intelligence community, they would potentially think of an information disclosure as being an exploit. If you ask the military, they would maybe think of denial of service as an exploit because, they really want to deny service to their adversaries. In crypto, typically we think of something like a side channel or maybe breaking a key with an algorithm as an exploit. And of course, in the hacking community, we typically think of control flow hijacks. Part of what we want to do is be able to formally characterize these sort of things, because right now, even if you go out and ask security professionals, they'll come up with different explanations of what it means to exploit a program. For example, I've gone out and said, well, here's an exploit. No, that's not an exploit. You don't hijack control. And I said, yes, but I can read any file on the web server. Oh, yeah, that is an exploit. That's an information disclosure. Now, for our particular project here, AEG, we've been focusing on control flow hijack because, well, that's the most exciting to us. But we do want to work on these other ones because they are important. A second challenge is we need to come up with formal methods that scale. When you analyze real programs, you have a very, very large state space. For example, here we have a program that iterates a loop while a to the n plus b to the n is not equal to the c to the n. Until very recently, we didn't even know if this loop would terminate for any value other than 2 for n. So how do we formally analyze this program in a way that we can actually scale? So that's one of the challenges we face, and we spend a lot of time actually answering this question for realistic sized programs. Now, we're not naive. We know that this is an undecidable problem in general, and we will never solve it for an arbitrary program. But just like everyone else, we want to be able to solve it for a practical number of programs. Now, our current prototype, as I said, take a formal methods approach. Really what we're doing is we're exploring the state space, we're finding bugs, and then we prove the bug is exploitable. It's really these 3 steps. In the first step, we explore the program state space to find bugs. And the output of this step is a Boolean formula that is satisfied by inputs that trigger the bug. Now for each bug we find, we determine whether or not it's exploitable. And the output of this step is again going to be a Boolean formula that's satisfied by control flow hijack exploits. Now step 1 and 2 output Boolean formulas. Boolean formulas are either satisfiable or unsatisfiable, and it turns out by construction a satisfying answer is an exploit. And we use a decision procedure to find satisfying inputs. Now the particular technique we use in step 1 to explore the program state space is symbolic execution, and we do this at the source code level. The reason we do it at the source code level is, well, it scales better. We'd love to be able to do binary level only analysis, but currently we're just not there. Now even with source code, we found existing symbolic execution techniques did not scale to the sorts of programs we looked at. So we developed a new technique called preconditioned symbolic execution, which you can read about more in the paper I reference at the end of this talk. After we determine that there's a bug using preconditioned symbolic execution, we do binary code analysis to determine what are the constraints necessary to exploit it. And we have a whole host of techniques to do this. So let me show you how it works on our running example. The first step finds bugs, and here we would generate a Boolean predicate like the one shown, where We basically say input.length has to be greater than size of ifr.ifr name in order to trigger the bug. So an assignment of values to variables that make this Boolean formula true would trigger the bug. We then do additional low-level analysis to reason about where we could put an exploit string. In this case, we're doing a code injection attack, as well as how we can overwrite control structures to transfer control to our particular attack string. So we call this the exploit condition. Of course, once we create this, we use technology to solve this formula to generate actual exploit instances. We use theorem provers. So our current status is we've done this on 14 different open source programs, and we've generated 16 different exploits. So in 2 of these programs, we found 0-day exploits. And essentially, we kind of found them by mistake. We ran our AEG tools that implement our techniques on these programs, and we ran them a little too long, and we found 2 new bugs. So I find this really encouraging because we found something that we didn't know was there. Now, there's a couple important columns here. First, the time to create an exploit. What you see here is in the best case, it took us about 0.7 seconds. In the worst case, about 20 minutes. More generally, what we find is our techniques either work, and they work quickly, like under 20 minutes, or you run off an exponential cliff. And this is actually a common thing you'll find in any verification. The second thing is what kind of exploit could we create? We're able to create local exploits as well as remote exploits now. And actually, that took quite a bit of work to be able to create remote exploits. Now, all of these programs are vulnerable either to a buffer overflow or format string vulnerability. And I'll discuss other types of vulnerabilities later on. So those were the programs we tested for our paper. However, we had an additional anecdotal success, and actually this success was my favorite. My students commonly enter capture the flag contests, which are like programming contests for security. And often you get questions like, can you create an exploit for this program? Our students in one of these timed competitions used our tools to solve the challenge. So I like this. I mean, it shows that our tools can be used outside just a simple research environment, and they could actually be used in a real timed contest. So we're doing this, and it has obvious offense applications. Why do we focus on offense? Well, in some sense, that's the privilege of computer security research. I mean, we need to understand what the capabilities of attackers are so that we can plan better defenses, because you know what? Offense informs defense. And so if we can demonstrate AEG, automatic exploit generation, is practical, even if we show it's just practical on 10% of the programs, is an important thing to know. Because you know what? In computer security, we typically assume attackers get lucky, defenders don't. So if an attacker get lucky in 10% of cases, defenders always really need to come up with defenses because they don't know where an attacker is going to get lucky. So what are some of our future directions? Well, currently we work on format string and stack-based overflows only. There are many other types of important vulnerabilities, and we would like to work on them as well. In particular, we're currently looking at heap and integer vulnerabilities, and we have some proof of concept code that we're trying to get to scale to realistic sized programs. We currently use symbolic execution to find bugs, and one of the things we'd like to do is really disentangle finding bugs from exploit generation. We'd like to be able to use other bug finding tools to find bugs and then employ our techniques to see if they're exploitable. Now, the particular symbolic execution techniques we use, the preconditioned symbolic execution I mentioned earlier, is more scalable in our problem setting than other previous symbolic execution techniques like CLE. And by the way, this is not a diss on CLE. CLE is a wonderful tool and we build on top of it. And we're continually pushing scalability, as are they. And so in fact, quite a bit of our focus is how can we make things like symbolic execution scale, because eventually we're going to need this, even if we have other bug finding techniques. And so I thank you. That's an overview of our research. I invite you to read our paper called Automatic Exploit Generation that's going to appear at NDSS 2010. You can find this paper and more information at our website at security.ece.cmu.edu.